Hello interwebs, welcome to Let's Fix Computers. I'm re-recording the intro to this video because unfortunately I kinda lost the footage on the last section of it. And I didn't actually realize until I finished editing everything that I had about 5 minutes ago. So kinda sad about that. However, what I do still have is the complete diagnostic of the laptop that I'm fixing. And so I think there was enough here to release the video as is anyway. So, in short, we have a Dell Inspiron laptop here that doesn't power on. When I plug in the charger, the light on the charger goes out. So, this is a classic sign that there is going to be a power fault in the laptop. And regular viewers will know what's coming next. It's the usual story. And I recorded another full walkthrough on how we go through and diagnose it and check everything. And I do get as far as showing exactly where the fault is. The bit that's missing is just simply me replacing the faulty component. So you'll have to take my word for it that I did that and it works. Anyway, let's roll the intro and get into it. There's the missing foot. I guess I could probably try and fix that. So, when the charger cuts out upon plugging it into a laptop, that usually means that the power management in the laptop is detecting a fault and deliberately cutting the power. It does this by shutting off the DC in MOSFETs, which we will find on here somewhere. So in order to find out if that's likely where our problem is, we're going to do some quick stabbing. So I'm going to put the multimeter into the ohms range, and we're going to look for a short circuit. So I'm going to start off by probing where the DC jack enters the laptop. So the DC jack is under the hinge here, and it's got a little wire coming around to here. So let's just peel this back. And I'm going to stab each side of the DC jack. And we see 332 kiloohms. It's 0.3 mega ohms. So that's not a short circuit, that's very high resistance. All right. So now I'm going to jump straight to CPU V core, which is here, I think, because here is our CPU, and there's a whole bunch of inductors and capacitors and some power stages here. So let's go to the capacitors that are nearest to the power stages. I'll give you a close-up of this stuff when I get there. So I'll put my black probe on a screw hole, and we'll just probe that guy there. There we go. There's our short circuit. Whoops, I fell off my ground. So 0.154 ohms. That's a nice deep short circuit on our main power rail. So let's get the motherboard out of this, and I'll start showing you how the power system on this laptop works. So this motherboard is an LA-F114P. And if you open Google and you type in LA-F114P space schematic, one of the very high up hits will be from the absolute mad lads at Badcaps forum. And you can register for a free account there. And the extremely helpful folks there will have a schematic. So if you want to follow at home, you can do that. Otherwise, I'll be showing you the one that I've just pulled up on screen. Ba-ba! And I'm viewing this through Flex Boardview from pldaniels.com. So the board on this one looks a little bit square. They don't show the cutouts, but if you look at the shape of the component layout on here, you can see that it is in fact the same shape as the motherboard. So there's our cutout there. So from here we can see the layout of the board, and we can also see all of the circuit diagrams here if I start scrolling through the schematic. Blah, 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 blah. So as we go through and discover things, I can show you the circuit diagrams and we can understand how this board functions. So let's start at the DC in jack. So there's two methods we can use to figure out where stuff is in the schematic. Firstly, if we look on the motherboard here, the actual DC in jack has got DC in next to it, and also like some of the components immediately next door to it are things like this jumper here. We've got PJP DC1, PQM01, and so on. So if I search for those designators in the schematic, that's going to land us in the correct general area. Or failing that, because I'm running Flex Boardview can actually get this stuff for me. So I'll just turn the board around to the same orientation that I'm looking at it. And if we look at the DC jack here, I can right click on this and search for part. And it will immediately search the schematic for that part. So here we now have the DC in section of the schematic. So let's have a look at this first. So what's going on here is we've got our DC in connector. And for that, we've got a couple of pins that go to ground and going through an inductor, which is interesting. Fair enough. There's a sense pin here, PSID, and that's how the laptop detects what charger is connected. And then we've got our positive pins here. So there's plus 19 volt ADPIN. So that's adapter in, shortened. So there's a bunch of bypass capacitors on the input there. We've got an input inductor, and then that becomes plus DC underscore in. So that's our DC in rail. So once our positive power comes in, it goes onto this pad here, and you can see there's a grid of vias there. So remember, a via is a path through the board. So it immediately goes through the board. So let's see what's on the other side. So that's coming up there, and then it goes through PL1. So because we've got a schematic in front of us, we can follow this along. So on the schematic, we've come in through the DC jack, and we've gone directly into PL1, and at this point we become DC in. And this is not shorted. This is high resistance, so all of these capacitors along here, this is all completely fine. So now we're on this big trace going around the outside of the board, and we go all the way down to here. So let's come back under the microscope at this point and see where we are. Now, if you watched my video breaking down the repair on the HP laptop, you should have a rough idea on what these guys might be. So these are our DC in MOSFETs. So this is the point where the laptop has the ability to switch off the incoming power. The MOSFETs are digital switches. So we're going through these pair of MOSFETs, through this one, then through this one, and these guys get turned on by their gate pins here and here. And then we go into this guy, and as you can see, we've got a current sense resistor. So big flat square package, usually with a number written on it, and you can see two little sense wires coming off of this guy, and those are going all the way back, and then they go through the board to somewhere else. That's going to go back to our power management chip. So once our power has gone through there, it splits and goes in two directions. It's going through those vias, and it's going off to here, and then going through those vias. So before we flip the board over, let's just see if we're shorted on this current sense resistor. So I'll put my black probe on a screw hole, and we'll just check if we're shorted here. And yes, we are. Okay. So there's a short circuit there. So just like with the HP laptop, we were fine up to the DC in MOSFETs, but immediately after the DC in MOSFETs, we've hit a shorted section of the rail. So what this now tells me is that we don't have a narrow voltage DC board here, because as soon as we go through those DC MOSFETs, we become the main power rail, because I found that short over here, and we'll get to that section in a moment. So we now have a short circuit on our main power rail, which is basically the entire power rail for all of the other things on this motherboard that need to be powered. So this board is a good example of this architecture because we can follow the power traces a bit further. So let's do that. So we went through these DC MOSFETs, and then I said the power split off in two directions. So firstly, let's have a look at where those are going. So if we follow it coming through this current sense resistor, going along here and into these vias, let's flip the board and see where those come up. On the other side of the board, we're coming up here. And then we go through this big old fuse and we go straight into JEDP. This is the display connector. So at this point, the display's backlight is being powered directly off of this rail. Now, this is kind of interesting to note because what this means is that the backlight rail here is always hot. So long as there is a charger plugged into this laptop or a battery plugged into this laptop, there will be power going through the display connector. This is the classic example of why it's really important to disconnect the charger and the battery if you're going to unplug the screen. So if you're replacing a broken LCD on this laptop, this is why you have to disconnect the battery, because this wire is always hot. Even if the laptop is turned off, there is still main rail power going through this connector. And because it's the main rail, it can carry a pretty beefy amount of current. So if you accidentally pull the display connector out slightly crooked and it just shorts across some of the other pins, you're going to dump the voltage on the main power rail, which could be 19.5 volts from the charger, into some of these other pins, which probably shouldn't get 19.5 volts put into them. If you're lucky, you'll just short it to a ground pin and pop this fuse. If you're unlucky, you short it into a pin that goes to the CPU and you kill the board. So if we don't go toward the backlight rail, we go into that little grid of vias. So let's flip the board and see where those are coming up. And those are coming up here. So they come up here onto this big power trace. And this trace is also going into two directions. Firstly, it's going down into this section here. And if we look a bit further along, we find the battery connector. So this is our battery charger circuit. And it's a bit more complicated than the HP we looked at. Because the HP we looked at had a narrow voltage DC architecture, the main rail was operating at basically the battery voltage. So all we needed to charge the battery was just simply a MOSFET that would allow power to go into the battery or not. But here, because we have a hybrid power system, the main rail could be anywhere from 11.4 volts for a 3-cell battery all the way up to 19.5 volts from the charger. So in order to charge the battery, we can't just dump 19.5 volts into it. So what we have are charging MOSFETs and discharge MOSFET. So the big MOSFET here, this allows power to flow out of the battery and into the main power rail if there's nothing coming from the charger. And then if we have charger voltage, these two MOSFETs here create a voltage regulator to put the charging voltage back into the battery. So that's our battery charger circuit. And you can also see we've got another current sense resistor here, so the system can detect how much power is going in or out of the battery. So coming back to our main power rail, if we follow this up, this is now going all the way up the side of the board. And the first stop here is at PLI11. And this is the capacitor that I measured earlier on. So let's just cut back to the wide view a sec so we can see what's going on. So here we've got our CPU, and this is our power system for the CPU. We've got a power stage here and here, and then this inductor is connecting the main power rail into this power supply for the CPU. And I measured that capacitor there. So let me show you this area on the schematic so you can see what this area is doing. So I'll search for PLI11 because that's the bit that actually connects us in. So on our board view, we're now here. And let's search for that. So on the schematic, that brings us up to our CPU V-core circuits. So this is repeated a couple of times because we've got two-phase supply with two power stages, and then there's our accessory supplies and system agent and stuff like that. So for our one here, we come in through this inductor from our main power rail, and then there's a bunch of capacitors present here. One of these will be the big one that we measured, a 33 microfarad 25 volt capacitor. And then there's a bunch of smaller multi-layer ceramic capacitors. So all of these are suspect because this is all shorted to ground, and these guys all have a path to ground. So any of these could have failed and caused a short circuit through to ground. Once we've gone through these, we go into the power stage chip. So this thing is going to be some kind of dual MOSFET package that acts as a regulator to our CPU power supply. So once we've gone through this, we become CPU V-core, which in this case is called VCC core. So we want to check that our short circuit is not the same resistance as this. So let's double check that. So under the microscope, we've come in through PLI 11. There's our big capacitor, our 33 microfarad 25 volt capacitor. Then we've got our bunch of ceramic capacitors here as well. And here's one of our power stages. So our power is coming through here with a bunch of capacitors bypassing it. It goes through this power stage, then through an inductor, and then eventually it goes all the way through into the CPU core. So could we have a problem with one of these power stages? Let's measure and find out. So with my black probe on ground, again, if we measure this capacitor up here, we see 0.13 ohms, really low, functionally zero. Now if we go through our power stage onto our core rail, we'll just measure the output here. And you can see here we've got 7.9 ohms. So this is pretty typical CPU resistance. Now you look at that and go, oh, 7.9, that's pretty low. That's normal. So when you're going through a big silicon package like this that eats a lot of power, you'll have low resistance here because it has to be able to carry a lot of power. So it needs to be low resistance to carry that power without burning out. But 7.9 ohms is not zero. So we know that there's nothing wrong. Where are we here? We know there's nothing wrong with our CPU or our power stages here and here because the resistance on the other side of the power stages is different to our short circuit here. So our short circuit is present here, but it stops here. So these capacitors are all suspicious, but this point onwards, we're fine. So these are all suspect. So we've checked our CPU supply. Where else is this going? It's also coming all the way up the side of the board, and it goes all the way up and round, all the way up and round. It's going all the way over the top. Is it coming through there? Not quite. Over the top, comes all the way back around to the DC in area again, and it stops at this guy here. And this is probably our memory power supply. So let's check this. So that is PU301. So what is this? What are we looking at here? So we came all the way up the side of the board, all the way over the top to this guy here. So let's search for that. And PU301 is... it's our 3.3 volt rail. And somewhere around near it, we're also going to find that this connects to our 5 volt rail. So here we've got the 3.3 volt rail and the 5 volt rail. And again, these are going to be driven directly off the main power rail. So we should check both of these. We should find out if either of these are shorted. Because let's say that PU301 here had gone thermonuclear and had just shorted straight through. Let's say this capacitor here had failed and just shorted the 3 volt rail down to ground. And in doing so, it had then overloaded its power regulator and cause this guy to short all the way through. That now means that our main power rail has now shorted through the 3-volt regulator, through a faulty capacitor down to ground. And this could mean that the main power rail isn't the problem, the 3-volt rail would be the problem. So we should check the 3-volt rail and the 5-volt rail to see if they're okay. So let's do that. Let's head back to the board. So with my black probe on ground, we can check the input to PU301 here. You can see the big trace coming in here, and we'll find that this is going to be shorted to ground because it's on the main power rail. However, is the output from it shorted to ground? So we'll check the inductor on the other side. That looks like it's coming down out here and into here. And on the output, we've got 7K, 7,000 ohms. So no, the 3.3 volt rail is not shorted. So this isn't our problem. However, again, we've got multi-layer ceramic capacitors around here. So these guys are suspects because they are on the shorted rail. These can be giving our main power rail a path to ground. So those are suspicious. So if PU301 is our 3-volt regulator, which one is going to be our 5-volt regulator? Well, if we look further down on the schematic, we can see that it is PU501. So where is PU501? Well, I can right-click on that, or I can search for it on the board view, and we can find that it's up in the top left. So there is a 3-volt regulator. Here's our 5-volt regulator. So on the board, we're going to scooch over to the left here, and there's PU501. Now, I'm not sure why this one is taking a slightly more funky entryway in, because you can see our power is coming in the side here. I'm not sure why it doesn't connect directly across to there, because that's the main power rail, but it doesn't really matter to us. We know where it goes. We know it's powered from the main rail. So let's measure the input, and we'll find that again, there's our familiar short circuit again, because the main power rail is shorted, and the output from it is also not shorted. That's at 14 kilo ohms, 13.9. So there's no problems with the 5-volt rail either. Cool. But of course, once again, we've got input capacitors here and here and here. So we've got more suspects, more things that could be the problem. So now we've kind of done a tour of the board here. We've come in through the DC in jack, and we've gone on a wacky adventure down to the battery area, and then we've come up past the CPU power area and up to the secondary rails, the 3-volt rail and the 5-volt rail, and we've found that our main power rail is got a dead short to ground, but all of the secondary rails, those all seem to be fine. This is good news for us. It means that our fault is going to be directly on the main power rail. You don't want to find faults on the secondary rails, because that means that something on the secondary rails has probably gone bang. If you've got issues on the 5-volt and 3.3-volt rails, there is a good chance that that could be powering something like the PCH. That's the smaller die on the CPU here. And if we had problems with the CPU V-core power stages, that probably means our core is dead, which would also be sad news. But all of our secondary rails look fine, so this is good news for us. So the only problem is now is we've got capacitors all over the place on this main power rail, and we don't know which one it is. So the first thing we're going to do is we're going to do a close-up inspection of some of those capacitors. I'm not going to spend too much time looking through all of them, because our fault really could be anywhere on the board at the moment. We haven't narrowed it down very much because the main power rail goes to many places. So I'm kind of just going to give the board a very quick glance over, but there's so many capacitors to check that the chances of us actually spotting the cracked one aren't great. But, you know, we'll have a look at a couple just in case we get lucky. So let's have a quick look. So this is kind of where our main power rail comes up from the DC in MOSFETs. There's no capacitors around there, so we don't super care about them. So we're looking at these little ceramic boys around here. We're looking for something that has an obvious crack in it, or a hole or something like that. when we see it, it will probably be obvious if we're going to see it anyway. And I'm not seeing much there, so I'm going to come up here, back to CPU vCore, looking at these guys. They look okay. The big tantalum, you know, that doesn't have a hole in it. Those guys look okay. Sometimes you'll only see defects on the side of the capacitor, and it can be real hard to get the board at the right angle to spot that. Let's come up to our 5-volt rail. Those guys seem okay. Over to our 3.3 volt rail. Again, those look okay as well. So, not really seeing any smoking gun. At this point, I'm happy enough that we can't see it with the naked eye. So now we move to power injection. So we don't know which one it is, but one of these capacitors has turned into a wire and is connecting our main power rail down to ground. If we manually push power into it with a DC bench supply, power that the laptop is not capable of controlling, then that power will go through the faulty capacitor or component, wherever that is, causing it to heat up. So we're going to inject power onto the main power rail and use the thermal camera to look for something heating up. And that will reveal our faulty component. So let's get the probes. I'm going to connect my ground crocodile clip onto this USB port so it's got a nice big biting connection to a ground point. And I've got my power supply set up for 1 volt and 3 amps. Now before we inject, we once again need to consider our injection checklist. So these are our checks we go through before we try and inject power. So, number 1, why are we injecting power? Well, we have a shorted component and we want to push power through that component to cause it to heat up and reveal itself to us. Number 2, do we know where we're going to inject? Yes, we're going to inject on the main power rail because the main power rail is shorted to ground and it shouldn't be. It should be high resistance. So we're going to inject onto any of the points on the main power rail. So in this case, I can just go off the back of any one of these large components where we've seen our short circuit. Number 3, could there be anything else that's shorted other than the main rail, something downstream, like a secondary rail or something like that? Well, we checked our secondary rails, we checked the 5 volt and 3 volt rails, and those were not shorted. We also checked vCore, and CPU vCore is not shorted. So we've no reason to believe that the power we inject will go anywhere other than the main rail. And number 4, could anything be damaged? No, because we're injecting at 1 volt, which is fairly safe, and we know that that's not going to go into our CPU because none of the secondary rails are shorted. So we're good to go. Let me turn on my thermal camera. So I've got my infrared P2 Pro set up and we'll just start recording that video so I can just bring up the handy cam on screen. And I'm going to stab the big capacitor. So let's see what gets hot. Oh, it's right below where I'm stabbing. Okay, something around this spot heated up. So what I'm going to do now is I'm going to pull back and just probe it somewhere else just so I can see that a bit better. So I'm going to probe up at the input to the 3 volt rail. It's the same thing. We're injecting on the same rail. I'm just poking at a different point on that rail just to move my hand and my probe out of the way. There we go. Down there. Okay. So it's somewhere in the CPU vCore area here. So I'm going to come down on the close-up view now, and we'll go for a nice macro shot. So I'm suspecting one of these capacitors here at the moment. Let's see which one it is. And there we go. It's the one on the right. Now, if you look carefully here, you can see that PLI 11 is also getting a little bit warm, because it's passing those 3 amps. 3 amps is going through PLI 11, which is why that's getting a little bit warm. But the actual capacitor itself, that's the guy going nuclear, because that's the one passing it to ground. And while PLI 11 is good to handle this kind of current, that capacitor is not happy taking 3 amps. So that guy's burning up. So what we saw there was this guy getting super hot. And let's just tilt up onto the side and just see if we can spot any issues with that. There we go. You can just see we've got a hairline crack in the side of that guy. Now, whether it was there before or not, we'll never know. I didn't spot it originally. However, again, the problem is when there's so many different capacitors that it could be, you can spend an hour staring at the side of every single capacitor on the board if you want. But at this point, we've now found it, and it was either already cracked or it cracked when we dumped 3 amps into it. The point is, that guy's dead. And now we can check on our board exactly what that is by looking here. So that's this guy here. It's PCI 01. And if we jump, and if we search that up on the schematic, so that brings us back to our CPU power rail that we were looking at earlier on. And it's this chap on the end here. So that's a 10 microfarad 0805 25 volt capacitor. So our main power rail comes in through here. It goes through PLI 11. And then as soon as it gets to the end of this capacitor bank, it gets pulled down to ground through this guy. And by extension, that pulls everything on this 19 VB rail down with it. So we're going to desolder that from the board, replace it, and this laptop will be back in the land of the living. And that's where the tape ends, folks. So unfortunately, the last section where I actually replaced that dead capacitor, I kind of lost the footage for that. Normally I would have a backup until the video is completed, but in a moment of rashness I emptied out all of my whole video folder on the recording machine, thinking that I was done with everything there. So don't have that backup. Anyway, I hope you enjoyed the diagnostic work anyway, and I'll see you guys in the next video. Thank you very much, and I'll see you soon. Bye.